Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
We'll be looking at virtual work for this particular problem. We want to determine the angle theta for equilibrium, the equilibrium position, okay, as well as the stability for that position. To solve the problem, we will determine okay the potential function and differentiate it with respect to uh, theta and set it to zero, solve the resulting equation, okay, and determine the equilibrium position and theta. Of course, we will also differentiate further the position function. Sorry, we'll take a second derivative of that function, of the potential function, and and solve it, okay, to determine solve the resulting equation to determine the stability. Okay, all right. We have this. This is the spring force. There's a spring there, acting upward there. This point A, and this is point okay. This point B. All right. We have the distances are given. Okay. Of this. Okay. Length BD is given, all right, from the question. So we can just, and this is angle theta, and therefore this is also going to give us theta, okay. So we can just determine the, this is W, and the mass is given for that, all right. So having known this, we will just go for the bar, which is AD, bar AD, okay, and determine this have y. You can see that we are going to have a negative gravitational potential there, energy, because the datum here at A is hard, and the center of gravity of that bar AD area, the way to act through, so that y is going to give us it's really bar is going to give us we are given AB to be 0.5, okay, and we're also given BD to be 1. So if we add this, we're going to have this divided by 2 cos theta, all right? So that's what we're going to have for that. Then we can also, with that, therefore, we know that V, which is the, uh, sorry, VG, V source with G rather, is going to give us it's equal to W, okay, Y, all right. So we can consider the spring. If we consider the spring, of course, the spring is unstretched at 90 degree. So the distance S, uh, which is that, is going to, which is the displacement, is going to be uh, 0 0.5, 0.5 cos theta, okay, minus 0.5 cos 90 degrees, 0.5 cos 90 degrees, okay. And of course, this is the same thing as S is equal to 0.5 cos theta, 0.5, 0.5 cos theta, okay. All right. Now we can also for the gravitation, so the elastic potential B subscript E is going to be equal to the spring stiffness times S squared over 2. All right. You can now, okay, so we know that the potential function is v subscript g plus v subscript e, all right, which is equal to uh, so we can just plug in our values in there. This is w, the same thing as w times y, which is minus 1 9. Okay, if we multiply the mass, which is 20 kg times 9.8, we're going to have this 196.2, then y. So everything is going to be, we got y to be equal to 0. 0.1. We divide it, we're going to arrive at 0. Y will give us, everything is going to give us 0.75. When you do solve that, do your multiplication, addition and multiplication, and division cos theta. Okay, so you have this. So that's what you're going to have for that one. Then you will now add for the elastic potential. So the spring stiffness is given as 2000 Newton per meter. Actually, the question is 2 kilonewton per meter, which has been converted to Newton per meter, times 0.5 cos theta. Now this is S. Okay, so you have to square it. You square it according to the cos theta. All right, so we have that now. So when we solve that out, we are actually going to have a v. It's going to give us a minus 147.15. Okay, cos theta. Cos theta plus 250. Okay, cos squared theta. All right. So if we take consider the equilibrium position, do our we have for equilibrium position, equilibrium have the v d theta is going to give us this value 147.15 sine theta, all right, minus 250. Okay, 150 sine 2 theta, sine 2 theta. So we have that. And of course, notice that sine 2 theta is 2 sine theta cos theta. So if we do that, we are going to arrive at this to be, of course, when we do that, and we'll have sine theta to be common to the part. You can see that it is to become common by the time you apply sine 2 theta to be equal to 2 sine theta cos theta. Have this 147 minus 147.15 plus 500 cos theta, 500 cos equal to 0. Remember that it must be equal to 0. So let's put it there. All right. So when you solve this now, you're going to have for sine theta, you have sine theta to be equal to 0, so that theta there, when you take the arc sine, is going to give you 0. Then we also have, when we solve that again in there, you have cos, you arrive at cos theta to be equal to 0.2 0.2943. So by the time you take the arc cos, you're going to arrive at theta also to be equal to 72.9 degrees. 72.9 degree. So these are the equivalent positions, 0 degree and 72.9 degrees. Therefore, for stability, we can determine the stability, okay, using taking the second derivative of the function. So we have this, okay. So if we do that, if we consider when theta is equal to, we consider when theta is equal to 0 degree, okay, we are going to arrive at this to be equal to, okay. So but we need to differentiate that first. To differentiate that, we are going to have 14. Okay, so let's just differentiate it first. 147. To take the second derivative first, we are going to have 147.15 cos theta, cos theta, okay, minus 500 sine cos 2 theta, cos 2 theta. All right. So if we now consider when it is theta is 0, so for I will plug into that relation, we are going to have the stability, the second derivative. Consider when theta is 0, we're going to have this to be equal to minus 352, 352, 352.9, okay, point 9. So you can see that this is clearly less than 0, which is shows that the equilibrium here is unstable. Stable. Okay. Then we can also consider when theta is equal to 72.9 degrees. Okay. So for that also we are going to have the squared v over the theta squared to be equal to 456. For when you plug that uh, position, the angle into the second derivative, the result for the second derivative, okay, relation there, we are going to have this. You can see that this is clearly uh, uh, greater than 0. So for this position, it is stable. So these are the equilibrium positions as well as their stability, stable and stable respectively.